Hello. So I hope you guys got the answer key that I posted for the homework. So it was inside the YouTube video with the recording of the class. So that would be in the description of the video. So hopefully you found it there. Hello. So it seems like every week the amount of people that take this class are getting smaller and smaller. And I know that the stuff you need to grasp in this class is very, very difficult. Physics is one of the hardest sciences to understand. So the fact that you guys have gone this far already is already achievement. All right.
Hello.
Hey.
How could it not work?
I hope you guys found the key for the homework. And I wrote out descriptive solutions for the problems as well. So, but if you do want me to explain any of them right now, then feel free to ask and I will do that. All right. Maybe I'll wait one more minute because like it seems like people come in just a few minutes late. All right. Hello guys. I said this before, but if you just came in, I would like to say that it seems like a lot of people have been quitting the class. And I understand that because this is very hard to grasp. Physics is a very hard science. It's the hardest one, in my opinion. So the fact that you guys have gone this far, it's really a great accomplishment. All right. And if you're kind of struggling right now, don't worry. The more problems you do, the better practice you'll get. And eventually, it's going to be a piece of cake for you. You just have to put in practice, like with anything. So now, it's 8:01. Let me share my screen here. So week 9, as you can see on the PowerPoint, let me first share my computer sound. So week 9 of physics, we're going to be talking about all about the conservation of mechanical energy. We're going to be talking this entire class about this one concept. All right. So what are the topics? We're first going to talk about the conservation of mechanical energy, and then we're going to go and talk about something else called power, which is not really that much related to the conservation of mechanical energy. And so the bulk of the class is going to be about the conservation of mechanical energy. And then in the end, we'll do a little bit about power. Okay? So the conservation of mechanical energy. So last week, what we went over is we had different types of energy. We have kinetic energy, we have gravitational potential energy, and we have elastic potential energy. So we have all these different types of energy. So what is the conservation of mechanical energy? Well, you might have heard the saying that energy cannot be created nor destroyed. And that's true. The amount of energy in the universe is set. You cannot create more energy. You cannot destroy any energy that exists. There's one set amount of energy that exists in the universe. Could be like, I don't know how much it is, but it's some kind of value X, and that's the amount of joules of energy there are in the universe. And this total amount of energy, it can become in different forms. As we know, there are a lot of different types of energy. There's kinetic energy, there's potential energy. And this energy can be transferred between these forms. But the total amount of energy that exists always stays constant. So this is the conservation of energy. If we want to write this in an equation form, we have the initial energy as E initial that equals the final energy, E final. All right, so the amount of energy we have in the beginning is equal to the total amount of energy we have at the end. All right. So once again, this is all based upon the fact that energy can't be created or destroyed. So this is basically what the conservation of mechanical energy is. All right. So if we want to define the total amount of energy in terms of the types of energy we've done, like kinetic energy, gravitational potential, and elastic, well, what we can do is we can write, well, the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic potential energy equals the final kinetic energy plus the final gravitational potential energy and the final elastic potential energy. All right, so this is one way you could use to describe just the conservation of mechanical energy. The total amount of energy we have in these forms in the beginning will be the total amount of energy we have in these forms in the end. It's just that the energy might be transferred between these forms. It might turn from kinetic into elastic potential energy. It could turn from elastic potential energy to gravitational potential energy. Okay, so this might be a lot to remember. So what I would just recommend doing is just saying, hey, the amount of energy you have in the beginning is equal to the amount of energy you have in the end. So there's one problem with this formula here. Well, what's that problem? Well, let me give you an example. If we have a box sliding on a table, it's going to have some kind of initial kinetic energy. This is the E initial we have in our equation. In the end, it's going to come to a stop. So that's our E final. So what is the energy this box has? It has no kinetic energy because it's not moving, right? It also has no gravitational potential or elastic energy. So where did that initial kinetic energy go, right? According to this equation, this doesn't make sense. Well, what made the box stop? Well, that's friction, right? Friction makes the box stop. So there is a frictional force acting here. Friction. All right. So when the box travels a distance, friction will do work, and work is a type of energy. And the energy that friction creates of objects rubbing together, if you were to rub your hands together, what does that create? Your hands get warm, right? So frictional work creates heat, and heat is a type of energy. So not only do we have kinetic energy, gravitational potential, and elastic potential energy, we have heat energy as well. And heat energy is created by the work done by friction. So in the end, what we have is the heat energy, the energy of heat. So initially we have kinetic energy, and all that kinetic energy was turned into heat energy. So what is the value of this heat energy? Well, it's just the work done by friction. It would just be frictional force times distance. So how will we fix the formula we have here? Well, we have an initial amount of energy, right, in our various forms. And in the end, we also have that kind of energy. But if there's friction involved in the process, then heat was generated by the friction, right? So we have to include the heat component of energy in our equation as well. Okay? So we have 4 different types of energy, actually. We have kinetic energy, we have gravitational potential, and elastic potential energy. But we also have the heat energy created by friction. And the work done by the friction equals the amount of heat energy produced. So when you do problems, you have to look out for all 4 of these types of energy. Okay? So how would you solve problems involving the conservation of mechanical energy? You would take an initial point and you would calculate all the energy that's found in that initial state. And then you take the final point and you calculate all the energy that's found in that final state. And in the final state, remember to note the heat energy made by friction. Okay, so that's basically the gist of the conservation of mechanical energy. So it's basically the initial amount of energy you have will always be equal to the final amount of energy. Okay, any questions? All right. Before we go on to problems, I would like you guys to watch this video here. So can you guys hear the sound?
I am such a strong believer.
So before we start the video, can you guys hear the sound? I just want to make sure. Okay.
Of the
Take a look at this video.
conservation of mechanical energy, that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
So if you don't know who that is quite a famous physics professor at MIT. His name is Walter Lewin. And I think this is just a really cool demonstration of the conservation of mechanical energy. So when the pendulum is at its highest point, that's the total amount of energy it has. So when it comes back, it cannot go any higher because it can't have more energy. You can't create more energy, you can't destroy any energy. So why does it actually go lower? Well, that's because there's some kind of friction involved when the ball is swinging. There might be air resistance, there might be all that kind of stuff. So that's where the energy went. Okay, so I think that's pretty cool. So now let's do some problems about the conservation of mechanical energy. So how do I go on? All right, so we have these 3 problems here. I'll give you guys 5 minutes to do these. And when you get your answer, please chat that to me. Oops. Doesn't seem like I'm able to see the chat, so if you'll excuse me for a moment, let me stop sharing. Sorry about this. So let me try to fix this. Let's go back to these problems. Let me see. But I can't really see the chat right now. Never mind. So since I'm not able to see the chat, when you get your answer, I don't think I'll be able to see it. So hold on to your answer, and when I explain it, then you might be able to, you'll be able to check if your answer is right. Oh, I can see the chat now. So once you get your answer, feel free to chat that to me, and I'll let you know if you're right or not. All right, how about one more minute to do these problems? Because we have a lot of problems, practice problems to go to. So if you're struggling a little bit right now, when I go over the answers, you might be able to understand it a little better. So I have a lot of problems prepared, and that's why I want to get through them. All right, so because I have one more answer, let me see if that's right. So I'm going to explain these now. So for the first problem, a ball falls from a table of height 1.5 meters. What is its speed before it hits the ground? So we have a ball from a height. It has some kind of gravitational potential energy, right? When something is higher than the ground, then it has stored gravitational potential energy. So the initial state we have is the ball up on top with just gravitational potential energy equal to mgh. So that's the initial energy. So let's write that here, mgh. Now the final energy. What's the final energy? Right before it's going to hit the ground, the ball has used up all its gravitational potential energy, and all that energy is stored in the form of kinetic energy, 1/2 mv squared. Cancel values here. V will equal to the square root of 2gh. So what's that going to be? That's going to be around 5.4 meters a second. Okay? So alternatively, you could have found this using the kinematic equations. This would have been completely feasible in that way as well. So energy is just another way to solve these problems. So oftentimes in physics, there are multiple ways you can use to solve these problems, okay? So now for the next one. In the experiment, Professor Lewin's pendulum was attached to an 8.8 meter long string. If he raised the pendulum so that the string made a 35-degree angle with the vertical when released, what was the maximum speed of the pendulum? So let's look at the initial position here. We have an initial position where the pendulum is raised at 35 degrees to the vertical. And the string is 8.8 meters long. So when it's in that position, compared to the bottom point, it's going to be at some kind of height above the ground. It's going to be higher above the ground. And when it reaches the bottom point, all that stored gravitational potential energy will turn into kinetic energy right here. Okay, so this will be the point where the speed is maximum. So this is the point where all the gravitational potential energy has turned into kinetic energy. So what is this height h? How do we find this? Well, if we make a right triangle here, we can see that this length is 8.8 times the cosine of 35. So to find this length, we just do 8.8 minus that. This will be our h. So the initial is mgh. That equals 1/2 mv squared. If we cancel again, v equals the square root of 2gh. So let's first solve for h from this equation. So what's that going to be? 1 minus the cosine of 35, all times 8.8. So h is around 1.59. So we plug this in, we have times 9.8 times 2, take the square root, 5.6 meters a second. Okay? So this is just another way. This is just another problem about gravitational potential energy into kinetic energy. It's just that there was an extra step you had to take when solving for the height. Now we have another one. You drop a textbook from a height of 3 meters above a soft layer of snow. The book sinks 1 meter into the snow before it stops. The mass of the book is 5 kilograms. What was the force of the snow on the book? So let's look at initial and final positions again. So what's the initial position? Well, this ledge is 3 meters high. And then we have 1 meter layer of snow. And the book is right here on top. So that's the initial position. What's the end position? The end position, the book is beneath the snow. It's 1 meter beneath the snow, and it's stopped. All right. So what's happened here? Well, let's compare the initial and final positions, right? So initially, we have gravitational potential energy, and this energy is being released. And then in the end, why does the book stop? Well, the snow does work on the book, and there might be frictional forces involved that create heat when the snow is stopping the book. Okay, so what is this going to be? This is going to be the initial potential energy we have has all been converted to the work done by the snow. Force times the distance. So what is the distance that the snow will be able to apply this force? 1 meter. So F times 1. So what's mgh? Well, the height is not 3 actually, because when we compare the beginning and the end points, the beginning point is actually 4 meters higher than the end point. So instead of 3, we use 4 in this case for our gravitational potential energy, mg times 4. So in the end, it's just mg times 4, so 5 times 9.8 times 4, and the force will equal to 196 newtons. All right, any questions? Okay, so we have more problems here. So take around 3 minutes for this one. So when you get your answer, please chat that to me. And if you want to explain one of the problems, then let me know as well. All right, so Tyler has gotten the right answer, and he's going to be explaining this problem when it's time. All right, so now I'm going to let Tyler explain this problem. So go ahead.
So since all of the energy is conserved and you have a spring and it's also just moving at a constant speed before the collision, you have the energy equations 1/2 mv squared equals.
Would you like me to write it?
1/2 m squared equals to 1/2 kx squared. So then you substitute m for 5 kilograms and k for 150 Newton meters, x for 0.1 meters, which is 10 centimeters. And then solving for v, you get about 0.5 meters per second.
Yep, that's the right answer. So you basically compare the beginning and end positions here. So in the beginning, the box is zooming towards the spring. All we have is kinetic energy. It's shown that there. And in the end point, the spring has been compressed and the box has stopped. So all the energy we have now is in the form of elastic potential energy. And then you would solve that for the velocity. Okay, nice job. So we have 2 more problems here. So I know this is a lot, but to get the conservation of mechanical energy in your head, you have to do a lot of problems about this. In the second problem, I want to refer to the length of a ramp. Whenever you talk about length of ramps, you talk about this distance here. So this distance is 5 meters. So when you get your answer, please chat that to me, and I'll let you know if you're right. All right. How about one more minute? All right. So if you're not quite finished on the second problem yet, you can continue doing that while I explain the first problem. So a box is gliding on a frictionless surface at 8 meters a second, and it suddenly encounters a stretch of rough surface with a coefficient of friction 0.3. And if it eventually stops, what minimum length did the surface have? So let's look at initial and final positions again. So we have a box zooming towards this rough surface at 8 meters a second. So that's our initial position. And the initial position is the box has some kind of kinetic energy. So what is the final position? The final position is where the box has stopped along this rough patch of maybe it's concrete or something. So we have initial energy, and where is the final energy? The box is not moving. There's no potential energy or anything. So where did that energy go? Well, remember, when stuff rubs, when frictional force acts, the work done by friction will create heat energy, and that's where the energy went. So the initial kinetic energy has been transferred into heat energy, and this heat energy is equal to the work done by friction, which will be mg mu, which is the frictional force, times the distance in which this was applied. All right, so if we cancel stuff, we get distance equals v squared over 2g mu. If we solve this, we're going to get something like 10.8 meters, I think. All right, now for the second problem, a box starts out at the top of a ramp inclined at 30 degrees to the horizontal. The ramp is a length of 5 meters and the coefficient of friction is 0.1. What's the box speed as it leaves the ramp? Well, once again, let's look at initial and final positions here. The initial position, the box is up high. It has some kind of gravitational potential energy. And in the end, the box has left the ramp. It's moving at some kind of speed. So in the end and in the beginning we have potential energy. In the end, we have some kind of kinetic energy. But there's also friction acting in the system. We can't forget about friction. And where is the friction? What is the friction doing? The friction creates heat energy, all right? And this heat energy takes away some of the potential energy so that the eventual kinetic energy is not as high as it would be. So it's almost like the friction is stealing energy from the potential energy and creating it into heat, all right? So in the beginning, we actually have heat energy too. In the end, we have heat energy along with kinetic energy. And this heat energy equals friction force times the distance in which it was applied. So the eventual equation will be mgh. So when we calculate potential energy, we only care about the vertical distance above the ground. And this h will be 5 times the sine of 30. Okay, so mgh. And in the end, we have friction force, mg mu cosine theta. Remember that equation from our lesson about inclined planes. And this will be multiplied by the distance. So what's this distance? This distance is the distance in which this force is being applied, which is the length of the plane. So we're going to plug this in as 5. And then we add the eventual kinetic energy. Okay, so when we plug values in and we solve, we're going to get something like 6.3 meters a second. Or maybe 6.4. All right, any questions? So basically, as we've seen with all these problems, we take an initial position, we take an end position, and we calculate the total amounts of energy that exist on both sides of the equation. We have even more problems here. So take around 3 minutes to do this one. This one's a little bit challenging. When you get your answer, please chat that to me, and I'll tell you if you're right or not. This one is actually quite tricky, so maybe I'll give you guys an extra 2 minutes to do this. All right, so I'm going to explain this one now. So there's a frictionless room where a tiny box slides along the floor at 11.5 meters a second, bouncing back and forth between two walls. No energy is lost during collisions with the walls. So then a mat of length 2 meters and coefficient of friction 0.2 is put in the middle of the room. And after some time, the box has stopped as a result of friction. And then it asks for where is the box stopping on the mat. So let's draw a nice diagram here. So we have a little box bouncing back and forth between the walls of a frictionless room. All right, so there's no friction involved. So if the mat wasn't placed down, then this box would go back and forth forever and ever. So now let's look at initial and final positions. Initially, we have the box with some kind of kinetic energy. So that's the initial position. We have kinetic energy. What's the end position? In the end, we have a mat, and the box has stopped somewhere on the mat. So where has this kinetic energy gone? Well, whenever we have friction acting, heat is created, and that heat energy equals the work done by the friction. So this will be the work done by friction. So how do we figure out how much work is done by friction? Well, this is just mg mu times distance. All right. So what does this distance actually mean? This distance is the total amount of distance in which the box has been rubbing against the mat. So what do I mean here? If the mat is placed here and the box goes over it one time, then the total distance is 2 meters because the mat is 2 meters long. If it goes back and rubs against the mat another time, then the total distance has now increased to 4 meters. If it goes back again, 6 meters, back again, 8 meters. So when we add up all this, this will equal to the distance, the total distance in which this mat has been on the mat, when the box has been on the mat. All right. So if we calculate this total distance, then we can analytically determine where the box will be on the mat. So how do we find this distance? Well, initial kinetic energy is 1/2 mv squared. This equals mg mu d. Canceling, d equals v squared over 2g mu. So in the end, if we solve, d equals 33.7 meters. So the total amount of distance this box was on the mat is actually 33.7. All right, so when the mat is placed down, the box is on the left side of the room. And when it passes over for the first time, 2 meters. When it goes back to where it came from, 4 meters. So for every multiple of 4, the box ends up on the left side again. So at 32 meters, the box will be on the left side. And so there's 1.7 meters left for the box to go. And when it encounters the mat again, it won't reach the other end because the mat is longer than 1.7 meters. And it's going to end right here, 1.7 meters from the left of the mat, from the left end of the mat. All right. So are there any questions about that? So this was just one of those friction and kinetic energy problems, except there was just this extra step where you would have to analytically determine where this box would stop on the mat. So this is one of 2 more problems I have. So this is actually very similar to the previous problem we just did a while back in the beginning of class. There's just this one extra step you have to consider. All right. So when you get it, please chat me your answer. I'll let you know if you're right or not. Someone's asked me whether we've done this problem or not before. We did something very, very similar previously at the beginning of class, but there's something a little bit different about this one. How about 2 more minutes for this problem? All right, so if you haven't finished yet, that's okay. So I'm going to explain this one now. Now this one is a bit tricky. So the horizontal spring, once again, lies on a flat surface, but this time there is friction on the floor. And the spring is once again attached to a wall. And a 5 kilogram box moves towards the spring at a high speed and collides with it. And in the end, the spring is compressed 10 centimeters. What was the speed of the box just before the collision? So initially, when the box is just about to collide with the box, just about to collide with the spring, it has some kind of kinetic energy, right? In the end, the spring has been compressed, and the spring has been compressed some kind of distance, x. So in the beginning, we have kinetic energy. In the end, we have potential energy. But this time, we have friction involved. And whenever the box rubs against the floor, heat is created. And we must consider this energy when we're calculating our energy equation, all right? So the heat is actually the work done by friction. And where does this work? Well, from the initial point to the final point, the box has moved a distance of x meters. So if we set up this equation right now, we have 1/2 kx squared. And now the work done by friction, mg mu, that's the frictional force, multiplied by the distance in which this force is being applied. From the end to the beginning point, the box has moved a distance of x, mg mu times x. So if we were to solve for v equals the square root of 1/2 kx squared plus mg mu x times 2 all over m. All right, and if we were to solve this, we would get 0.94 meters a second. So if you would remember the answer from the other problem, it was around 0.5. So as you can see here, more kinetic energy is required because some of the energy was lost to the heat energy by friction. Okay, so I'm going to skip this one, and I'm going to include this in the homework later. So we have this last conservation of mechanical energy problem I would like you guys to do. So this is one of those problems where it looks very innocent. It looks easy, but in the end, there's always some kind of trick involved with this problem. So let's see if you can get this one right. This is a really, really tricky problem. So how about 3 more minutes for this one? All right, so I'm going to go over this problem now. So a 2-kilogram ball falls from a 3-meter high ledge. So it's right here, and there's a vertical spring underneath this ball's path with an unstretched length of 50 centimeters. If the ball collides with the spring, how far will the spring compress? So we have a 3-centimeter tall ledge, and the spring is right here, length 0.5. All right. So in the end, this is the initial point. So what is the end point? The end point is where the spring has been compressed a little bit. It's no longer 0.5. It's compressed a distance x. All right. And all the gravitational potential energy has turned into elastic potential energy in the spring. So now, how do we calculate the amount of gravitational potential energy we have? Well, we can't just compare the top of the ball to the bottom of the spring. It's not 2.5. Because if we compare the initial and final positions of the ball, initially the ball is there, and finally the ball has not only fallen the distance of 2.5, but it's also fallen the distance x in which the spring has been compressed. So you have to include both 2.5 and x. All right. So it's just like that problem with the snow. You have to look at the beginning point and the end point and compare those heights. So not only do we have the 2.5, but we also have the distance x compressed. So what is our PE? So PEG equals PE elastic. So 1/2, never mind, it's not 1/2, it's mg. Well, what is h in this case? This is actually 2.5 plus x. So we have to include the distance where the spring is being compressed. This equals 1/2 kx squared. So in the end, you're going to have a quadratic, and when you solve this quadratic, you're going to have 0.39 meters. All right. So those were the problems about conservation of mechanical energy. So now we're going to be discussing power. Power is actually a much lighter topic, and I don't think it's going to take that long to describe. So what is power? Power in physics is defined as the work you do over time. So in modern society, we have a bunch of definitions for power. You could say, oh, the president has a lot of power. My English teacher talks about power in The Tempest. And in physics, the definition of power is the amount of work you do divided by the amount of time it takes to do that work. So one way you would visualize this is you have a staircase you need to climb up. The amount of work you need to do is set, mgh. That is the amount of work you need to do, all right? If you were to go up the staircase fast, then you would have more power because the time it takes to get up is less, all right? On the contrary, if you were to go up very slowly and you were to walk up, you would have a much smaller power output. Even though the work is the same, power depends on the amount of time it takes for you to do that work. So if you were to go up this hill fast, you have more power. If you were to go up the hill slow, you have less power. So another way we could describe this is using velocity. So what is work? Work equals force times distance. And then the power is force times distance over time. What is distance over time? Velocity. So force times velocity. So these are the two fundamental definitions of power. So power can be represented as work over time, or it could be described as the force you output times the velocity in which you are going at. So a common example is with the car. Your car is overcoming friction force and drag force. So that would be the force you would consider in the power equation, and then the velocity would just be the velocity of the car. So it would take more power for the car to go at a higher speed than at a low speed. So what are the units we use for power? Well, work is in joules, T is in seconds. So power could be represented as joules per second, or the actual unit we use is called the watt. It's a new unit, a watt. So 1 watt is 1 joule per 1 second. So this is the unit we most commonly use for power. Another unit we might use is the horsepower. Cars are often used in horsepower, and 1 horsepower is equal to 746 watts. Okay, so those are the 2 units you would use when you describe power. And then the 2 equations for power you would need to memorize are work over time and force times velocity. So in reality, in mechanics, which is the physics of things that are moving, you're not going to use power as much. But when you go on to electricity and magnetism, you're going to be talking about power a lot more. So, any questions about power? All right, so I have 2 little problems here that won't take that long. So when you get your answer, please chat that to me. So how about 1 more minute for these problems? And we're running a little low on time here. So if you need a refresher, power is work over time, or force times velocity. And then 1 horsepower equals 746 watts. All right, so I'm going to go over these problems now. So Carl climbs up a 5-meter high hill in 1 minute. If Carl weighs 68 kilograms, what was his average power output? So what was the work he needed to do? Well, he increased his potential energy, which means he did work of mgh. So to calculate his power, that would just be the work he did over the amount of time it took, mgh over t. If we calculate this, we have 5 times 9.8 times 68 over 60 seconds. So what's that going to be? It's going to be 55.5 watts. So whenever we do our calculations, we always give our answer in watts, and we're going to use watts in our equations. So now we can convert this to horsepower by dividing it by 746. So it's around 0.07 horsepower. So now, the last problem we have for today, a car motor has a maximum power output of 120 horsepower. If the car weighs 1,000 kilograms and drives on the road with coefficient of friction 0.24, what is the maximum speed of the car? So we have a problem that involves power and speed, which is velocity. So we're going to use the equation P equals FV. So what is the maximum power output? 120 times 746, because we have to convert everything to watts before we can use our equations. What is the force? Well, the force is the friction force hindering the car's progress, right? Because the car has to do an opposite force. Let's say this is the car. It has to do an opposite force to counteract the friction. This is going to be mg mu. And if we multiply this by its maximum velocity, then we will complete our equation. So if we plug values in here, we get 120 times 746 divided by 1,000 kilograms times 9.8 times 0.24. This equals our velocity. So let me calculate that real quick. It's going to be, oops, I think I did something wrong here. I think it's going to be 381 meters a second. All right. So that's how you do problems with power. Are there any questions about this? Alrighty. So that'll be it for today. As you can see, these problems might be a little hard right now, but if you do a lot of practice, they're going to get easier and easier as you do them. All right. So I hope you enjoyed today, and I'll see you guys next time. Bye.